So thanks. I'm not the only physicist at UCA, but thanks for the introduction. I mainly do astrophysics, and so I'll spend probably more of the talk talking about astrophysical evidence for the age of the universe, but we'll step through things here. So we had a nice outline of the scientific method this morning that we use logic, reason, and evidence to figure things out. And the question is, how old is that? So, as she said, let's figure that out together and look at the evidence that goes into this. Of course, people have choices in terms of how they want to go about answering this question. If you're a literalist in terms of your mythology, you may appeal to that. The problem with that is the stories are varied, the stories are vague, and inconsistent. So in terms of getting an actual number for how old something is, that's not a very good way to go typically. Of course, a better way to go is a non-cultural approach, just to go and look at the universe itself. If the clues are there, we'll be able to figure out those clues and put them together. And it actually turns out to be one of the great triumphs of science, that science has been able to put together various methods that turn out to give us a self-consistent answer to what the age of the universe is. So we use multiple methods and we get self-consistent results. So I'm going to start out outlining some of the methods, and then we'll get into talking about certain specific methods. I'm not going to talk about all the possible methods. That may be a misconception out there that scientists only are relying on one piece of evidence to figure this out. That's not the case. We try to check ourselves as much as possible. As scientists, we got to make a case. We got to make a case to our fellow scientists. Okay, we don't believe in anything. Okay, we look at the evidence and we try to make a case that we've got to defend. Now, one way that you can ask, one possible method that you can use to figure out the age of something or an event that happened in the past is if someone observed it and then wrote down what it was and when it happened. So you can go into the historical record for certain things. If enough details were written down and something was written down in terms of a date that we can reconcile with today's calendar, you can figure those certain things out. And some of this can be connected up with modern techniques of something called carbon-14 dating, which I'll talk about the basis of that later on. So the evidence out there is physical evidence. And there's physical evidence from biology, geology, physics, and this is kind of a long list. Not even this isn't a complete list of all the techniques that get used in biology, geology, and physics to figure out ages of things. On the left here, these are a combination of geologic and biologic methods. These are some additional biological methods, and these are a variety of different physics methods for analyzing the evidence to figure out the ages of things. And then there's a whole host of astrophysical techniques, everything from looking at meteorites, moon rocks, looking at what the sun does, looking at how stars evolve over time and change. We can actually look at radioactive elements in the atmospheres of stars that can be used to put limits on ages. In astronomy, the further away something is, you're actually looking back in time. So there's time folded into that when you're dealing with distances. And so things like the Hubble expansion rate and the cosmic background radiation are also tied to those, in addition to some additional physics. Now, in terms of the written record, of course, that has limits in terms of how far back in time that goes. Some of the oldest writing dates back to only about 5,000 years ago. Okay? This is an example of a Mayan glyph that dates back to about that time. If you're looking for a complete record of things that happened at that time, good luck there too. It's not going to be a complete record of all events and things that happened at that time. And when you're dealing with the Earth, rocks, things in the universe, this is going to be very limiting if you only use written records. It's also interesting that some of the mythological things also kind of date back to about that time. We were mentioning 5,000 years. It's interesting that it matches the written record here approximately, right? So how do we get started? When you're looking at the physical evidence for ages of things, you need something about the object that has in it some sort of chronological clock, some sort of physical evidence of something that's changed over time. And this is a classic that you're probably all familiar with, tree rings. Within a tree, you have an annual record of growth. So you know that each ring corresponds to a certain length of time, a year. Okay? And so you can figure out, for example, how old a particular tree is. If it's a live tree today, and you cut it down and take the core out of it, you can basically count rings and go back in time to figure out how old that tree is. And if you're dealing with trees from a particular location, the other information that's embedded in there is things like rainfall and weather. You know, in dry years, you're not going to have as much growth. In wet years, you're going to have more growth. And what's nice about that is if you've got multiple trees or even fossil trees from different times, you can match up the growth rate pattern. And you can have one tree that you can then link up with maybe a fossilized tree and another fossilized tree. And so you can have a chain of tree ring evidence, and people have used this to date things as far back as about 12,000 years. Okay, so we're pushing things beyond the 5,000 in terms of the written record. Another place on the Earth where you can get an annual kind of growth record is in the ice. So you have ice sheets, Arctic ice sheets, Antarctic ice sheets. You have each season a layer put down of ice, and that builds up over time. And so if you then drill a core out, you can actually count rings and go back in time. And these go back even farther than tree rings. These go back to nearly 1 million years ago, some of these ice core samples. Another place where you have layering is in the geology of the planet. You don't necessarily get yearly resolution here, but you do have different eras during the geology of the Earth where sediments get laid down over time and you get a build up of layers. And then you play the same sort of game you play with tree rings in terms of the stuff on the bottom had to be put down first, the stuff on top of that has to be younger, and so on. So the deeper you go, the further back in time. So at the very least, you have a relative record of time here. I have to do a little more work to put some absolute numbers on these layers, and that's where some of these other techniques come in. But at the very least, we have a relative date record. And people at first made some assumptions about sedimentary rates and things like that. You know, how long would it take for those layers to build up? And that gives you a rough start at putting some numbers on these. And again, the nice thing about this is also in those layers you find fossils. And so also in a relative sense, you can watch the evolution of life on this planet over time in these layers as well. So this becomes important in biology in terms of evolution as well. And again, this is the cartoon version of that. And again, same idea, the stuff lower down has to be from longer ago, and so on. So this is, in a cartoon sense, how biologists have put together the fossil record and the evolutionary record of life on this planet. Now, like I said, at a starting point there is you're getting relative ages. What you want to be able to put those layers on is an absolute time scale. And the primary technique to put those layers on a absolute time scale is this technique of radioactive dating, or using radioactive decay as a clock. Okay? The basic idea is there are certain isotopes of certain elements that aren't stable. And they will break apart and form a different isotope, and perhaps a different isotope of a different element. Now, the rate at which this decay happens for a particular isotope is a measurable constant quantity. So, if you have a sample, say a rock formed at some time in the past, locked in that rock are some radioactive isotopes, and those radioactive isotopes will do their thing, they'll decay at a known rate. And so from a very simplistic idea, what you want to do is look at the number of radioactive isotopes of that element you've got in the sample relative to the products it's turned into. And this essentially gives you a clock in your rocks by looking at that ratio of the radioactive stuff that's still in there versus the stuff that it's turned into. And so you can see over time, you lose some of these radioactive ones to the daughter products, and you wait a certain amount of time, you lose more, and the time interval for a particular isotope, the way they quantify this, is something called half-life. So if you're familiar with the term half-life, this is what they're talking about. It's the time it takes for half of the radioactive ones to decay. Okay, and then that sets the rate for you for that particular isotope. And so if you graph it up, you start out with a certain number of radioactive isotopes of a particular type of atom, and you watch over time, you lose those because they're turning into these over time. So the daughter products will go up in the sample, and the original amount of the radioactive one will go down. And this rate, this graph is exponential, so you get a halving of that at each half-life, and the number goes down exponentially. Now you can see there's going to be a limit to where a certain isotope will be useful. If you go too many half-lives down the road, you're not going to have anything left. So what kind of isotope you want to use will depend on how far back in time you want to be able to date the sample. Now for carbon-14, which you may have heard of before, uses this technique. Carbon-14 is unstable. It will decay into its products over time. And this gets used for biological samples because carbon-14 is continually produced in the Earth's atmosphere. Cosmic rays come in, hit the Earth's atmosphere, and it actually transmutes things into carbon-14. So you can see here, if a neutron hits a carbon-14, it will transmute it into carbon-14. We're getting too much feedback? Okay. You got this on?
Yeah, it should be.
Okay. Okay. So cosmic rays come in, hit the Earth's atmosphere, transmute some of the nitrogen-14 into carbon-14, and then carbon-14 isn't stable. It will decay at that at this rate for carbon-14. Again, this rate is measurable in the lab. Okay, so you can set that half-life. The half-life for carbon-14 is given there. It's another 6,000 years. So if you want to measure something that's millions or billions of years old, carbon-14 is not going to be your isotope of choice. But if you want to measure things that are, say, less than 60,000 years old, samples of wood and paper and things like that, this becomes a good technique. Because whatever the biological sample, whatever the organism is that's taking in the carbon, you know, you're taking in carbon-14 all the time, and while you're alive, in your body, you basically have a constant amount of carbon-14 in your body. And then once you die, you're not taking in any more carbon-14, and so the amount of carbon-14 in your body would go down, or the tree or whatever, once it dies. So that's an example of how the carbon-14 dating works. Now, like I said, you got to make the case that what you're doing is correct. Okay? One of the ways you can do this is, do you get consistent results with something else you trust? Okay? And I just talked about the tree ring ages. Trees are biological organisms. They die. The amount of carbon-14 in them is going to decay over time. Can you match up well the tree ring dating with carbon-14? And the answer is you can. This is what this graph here is showing. The more squiggly line here is tree ring age determinations, and then the straight line here are carbon-14 age determinations for samples of various ages. You can see they track really well, that you've got a good correlation between the tree ring age determinations and the carbon-14, so that gives you confidence that you can trust the results that you're getting. Now, like I said, if you want to measure things that are older than what carbon-14 allows for you to do, you got to pick isotopes that have longer half-lives. Okay? And these are some examples of some longer half-lives, isotopes that get used to measure some of the oldest samples here on the Earth, some of the oldest rocks. And so they're showing you the radioactive isotope and then the thing it turns into. And so you basically, again, are looking at what's left in the sample versus what it's turned into. This technique, when it gets used, they go a step further. They don't depend just on one isotope. They will do a ratio of a couple of radioactive isotopes. What the ratio will do for you is you don't have to know how many atoms were in the sample to begin with when you do the ratio, which is useful. So these are some examples of some of those isotopes. Well, what do they get? And so again, these are the ratios of radioactive isotopes used. Again, so that you don't have to know how much of that particular rubidium or strontium were in the sample to begin with. And for the Earth, it's a challenge to find really, really old rocks on the Earth. The Earth is geologically active. The Earth is making new rocks as we speak. Erosion processes are destroying rocks on the Earth as we speak, so it's really hard to find rocks that date all the way back to the origin of the Earth. But the oldest samples give us ages for some of the oldest minerals and rocks on the Earth, ages of around close to 4.5 billion years old using these techniques. So, is that consistent? That's just for the Earth. We live in a solar system. There are other rocks rolling around out there in our solar system. And we collected some of those rocks. Late 60s and through the 70s, early 70s, we sent people to the moon. And one of the things that they did is they brought samples back to us. And so let's play the same game and play it with moon rocks instead of Earth rocks. What sort of ages do we get? Now what's nice about the moon, it hasn't been geologically active for a long time. It's not making any new rocks. It's not really destroying any of the rocks that are there. So the rock samples you pick up on the surface of the moon are going to be fairly old to begin with. Now the oldest samples that they find, as you see here, also date back to that sort of 4.5 billion year range. Okay? So that's good consistency there. We've got two bodies in the solar system that we're getting consistent ages for here, the Earth and the Moon. Okay? What else? Well, there are some other rocks rolling around out there in the solar system. And some of these actually come to us. We don't have to go to them. These are the meteorites. These are the things that fall from the sky. And these are some examples of what some of these meteorites look like. And the nice thing about these is there's a second dating method that can be used on these in addition to the radioactive dating. Again, these are going to have radioactive isotopes that have decayed in them. But these are rolling around in our solar system unprotected from any of the radiation that's out there in space. And there's a lot of hard radiation out in space, things like cosmic rays. These are basically protons and neutrons at high speed that will slam into whatever's out there. And they actually slam into these rocks during their history and actually leave tracks and trails. So the older the meteorite, the more of these tracks and trails are going to be in the sample. So that provides a second check to the radiological dating of these samples. Well, what do we get? Well, surprise, surprise, we get a number very similar to what we got for the Earth and what we got for the Moon. These rocks seem to date back to the same formation time as the Earth and the Moon. You're getting ages there also in the neighborhood of about 4.5. These may even go a little bit older. So these are a very good sample of the early history of the solar system. So, just in terms of the Earth, we now have a good sort of timeline for the history of the Earth, from its formation, roughly about 4.5 billion years ago, through today. And then additionally, with the fossil record, we can see how, when the first organisms arrived, formed on the Earth, and how they evolved over time. And you can see that some of the oldest fossils date back when the Earth was only about 1 billion years old. So life has been on the Earth for the majority of the history of the Earth. Larger organisms are another issue, though. We've been here a smaller fraction of the time, larger organisms. Well, of course, there's another object in our solar system, right? The main object in our solar system, you know, over 90% of the solar system by mass is our sun. Okay? Now, we could make this assumption. We could assume that the planets and meteorites form at roughly the same time as the sun. Okay? So if we make that assumption that the sun has to be at least as old as the rest of the stuff in the solar system, you know, you can come to the conclusion that it's probably also about 4.5 billion years old. Or if you like scientific notation, billion is 10 to the 9. Now this is just an assumption. We're saying, okay, we've measured the ages of things in the solar system other than the sun. We're making the assumption that the sun is that old. Is there a way, is there some sort of evidence directly from the sun that would peg what its age is? Now, there is something that's been changing inside the sun. Okay? The sun has been changing in its core during its history. It's been doing this. In the core of the sun, the temperatures are high enough and the pressures are high enough for it to fuse hydrogen nuclei into helium nuclei. And this releases energy, and that energy gets radiated to us in the form of sunlight, which we all need to survive. But for the age problem, we've got something that is happening at a known rate. Basically, how much energy the sun is putting out per second is actually telling us how much of this is happening per second. Okay? So it's happening at a known rate. How much hydrogen is being converted into helium per second in the sun. Now the downside is, where this is happening is at the center of the sun. You look at the sun, you don't see the center of the sun. Okay, you see the surface. None of this fusion that's happening in the core, none of it's making it to the surface of the sun. It's still all locked up in the core. So you got a problem is, if we could see inside the sun and see how much hydrogen and helium is there today, we'd be able to figure out how long the sun's been fusing hydrogen. Okay? Well, it turns out there is a way to look inside the sun. And it's related to the same way we can kind of look inside the Earth. The Earth vibrates. Things like earthquakes will send vibrations through the Earth. We can study those vibrations, and it gives us information about the density of the Earth in its core, in its mantle, and so forth. Well, the sun has stark waves. The sun is a vibrating object. Those vibrations propagate through the sun, and how those vibrations propagate through the sun tell us information about the density inside the sun, and specifically the density of the core. And the density of the core can tell us how much hydrogen and helium is there. And then we can back out what the age of the sun is through these measurements. So what you have to do is, observationally, you have to measure how the surface of the sun is vibrating. And there is a special orbiting solar observatory that does that sort of thing. It looks at the red shifts, blue shifts of the surface, and it can then, if you apply the physics, you can figure out what the densities are like inside the sun. And in fact, you can look at this in terms of the density information. Tells you that the outer layers are about 70% hydrogen, 20% helium, which you can see directly as well, because we can spectroscopically look at the sun, and we can pull out what the quantities of hydrogen and helium are at the surface of the sun. And then this helioseismology then can probe the core interior, and the density information you get there tells us the core today has about 34% hydrogen and 64% helium. Okay? So about half of the starting hydrogen has been converted into helium. And since we know the rate that it's been doing that, we can back out a number, and we get a consistent number. We get a number of about 4.5 billion years old. So not only do the rocks in our solar system tell us the solar system's been around for about 4.5, the core of the sun is also telling us the sun's been around for about 4.5 billion years. So what's neat about that is we've got good, consistent results here that give us confidence that we're doing the right thing here. What about other stars? You can't do this analysis with other stars. The star has to be pretty close to you so you can actually resolve the surface and see those vibrations. Stars are too far away to do that sort of observation, so you can't do the helioseismology on them. Yeah, really, really big telescope you might be able to, but that's beyond the technology today. But you can do some of this radioactive dating on stars. Because one of the things that you can observe about stars is their spectra, and their spectra tell you what the star is made out of. And their spectral features from radioactive isotopes. And so you can play the same game we did with rocks. You can look at the ratios of these radioactive isotopes for certain stars, and that will give you a rough age determinant for those stars. And this applied to some stars, at least some of the oldest stars found using this technique, give us ages larger than 4.5 billion. Okay, we're getting ages in the ballpark of around 13, 14, 15 billion. Now, the error bars are pretty big on this technique. There's a variety of measurement uncertainties on these that fold in here, but it's giving us a rough ballpark, such that we can now start to address the question, not how old is the solar system, but how old is the universe. Okay? Now, if these numbers are giving us a rough estimate for the age of the universe, the sun hasn't been around for the entire history of the universe. Okay? The sun's been around for, rounded up to 5. These are telling us the universe has to be at least 12, 13, 14 billion, as opposed to 5 billion. Okay, is there any way to check this? Is there any other techniques that we can use? Again, this is just one technique. If there's just one technique, you're not as confident. But another thing that we know extensively about is how stars change over time. Stars form out of interstellar material, mostly hydrogen, some helium. They go through a process, again, of fusing hydrogen into helium. They eventually run out of that material in the cores. That forces them to go through some changes. This is kind of a cartoon of what the sun's history would be. So we're about halfway through this process. The sun will eventually run out of hydrogen in its core. It will become a red giant, and then eventually something called a white dwarf, basically the leftover core. Again, we know the rates at which things are happening in terms of fusion. That gives us information about how long a star like the sun can do this hydrogen fusion process. We said the sun was about halfway through, right? 5 billion. So we're looking at another 5 billion before it runs out of hydrogen. Okay? So the sun should be able to last a total of about 10 billion. And we're about halfway through. So if you apply that same idea to other stars of different masses, you can actually look at star clusters, which are a population of stars that form at the same time out of the same stuff. But because they form stars of various masses, these stars fuse through their hydrogen at different rates. Okay? So the hydrogen fusion rate for the sun is different than a star twice as massive as the sun. A star twice as massive is going to fuse through that hydrogen faster. So they're not going to be able to last 10 billion years. So what you're seeing here is a star cluster. Again, these stars all formed at the same time. And these are basically stars of different masses that are fusing hydrogen. And the most massive ones are towards the top here. Now, in principle, this line should extend up in this direction. There aren't any stars there because they've run out of hydrogen. And they've become these stars here, these giant stars. So, if these stars form at the same time, we can use this feature here to age the entire cluster. You know, what's the most massive star that's still there fusing hydrogen? That tells you the age of the entire cluster. And so if you look at different clusters, you'll see this is an older cluster. It's missing more of those hydrogen-fusing stars. And so where this turnoff is, that tells us again the most massive stars that are still fusing hydrogen, and that gives you an age for that cluster. So this cluster here is a mere millions of years old, where this cluster here is actually on the order of billions of years. And so you can cross-correlate this with the spectroscopic radioactive decay. And if you want to figure out the age of the universe, you want to pick the oldest clusters you can find in the universe to do that sort of analysis. And the oldest star clusters, using this type of analysis, give us ages again, somewhere in that 11 to 15 billion year range. So that's nice. We're getting consistent radioactive decay, ages, and this technique, which doesn't depend on that at all. It just depends on the fusion rates of these stars. So again, if you assume that the universe has to be at least as old as the stuff in it, the universe has to be as old or older than these ages we're getting from these stars. So that's two techniques. Of course, you want as many techniques as you can get your hands on to cross-check to make sure you're getting the right answer. There's no book that we can look up the answer in, okay, in science. So we have to look at as much evidence as we can. Now, another thing that we can look at that has something with a known rate of change are these white dwarf stars. These are the leftover cores of stars. And they're going to be hot at first, and they're going to cool over time. And we can, from basic physics, we can figure out the cooling rates for these white dwarfs. And so the cooler the white dwarf, the longer it's been cooling. And we know the cooling rates, so we can back out the ages. And this is a diagram showing you information about the brightness and temperature of a sample of white dwarfs. And the cooler they are, the older they are, you back out the numbers, and for these oldest, coolest, dimmest white dwarfs we've been able to observe, that gives us also an answer in the same ballpark, somewhere around 12 billion or so. So now we got three things pointing us to that same sort of answer. So if we put them together, along with one more that I'll talk about, these are the sort of answers we're getting from radiometric star dating, the main sequence turn-off dating, and white dwarf cooling, and their uncertainty. And the last thing we want to look at is something that's ubiquitous to the entire universe. Like I said earlier, the further away something is from you, the further back in time you're looking. The speed of light is finite. So, for example, if you're looking at the sun, you're seeing the sun 8 minutes ago. The nearest star to the sun, you're looking at it what it looked like 4 years ago. The nearest galaxy to our galaxy, you're looking at how it appeared 2 million years ago, and so on and so on. Okay? So the furthest, dimmest thing that you can observe, if you can figure out the distance, you've got some idea of how long that thing has been around, right? And so you use this look-back time idea. And of course, the further away something is, the dimmer it is, the longer you have to expose for. This is an image taken by the Hubble Space Telescope. That's parked in the Hubble Space Telescope at a patch of, looking at a patch of sky, opening the shutter, and then coming back about a week later. Okay? If you're into photography, you know that's a really long exposure time, right? And so that long exposure time, you're picking up things that are very, very dim. And in this particular image, you're picking up galaxies that are very, very far away, on the order of billions of light years away. Got it? So this is also putting limits on the age of the universe, right? That light can't be traveling for longer than what the universe has been around. And so the most distant galaxies are on the order of 10 billion light years away, therefore they have to be around for at least 10 billion years. So that's kind of the same number that we get. Now, in terms of these distances, if you want to measure the distance of a galaxy clear across the universe like this, you need something that's really bright that you know the intrinsic brightness of, so that you know that it's a certain wattage light bulb, and then you measure how bright it appears, you can back out the distance. One thing that's really bright that we know that the intrinsic brightness of are supernova explosions. And they get as bright as the galaxies in which they reside, and that allows us to pick them up with the Hubble Space Telescope and other large telescopes at distances of billions of light years away. Here's another example of a supernova going off in a galaxy. The downside here is you can't just pick any old galaxy. You got to pick the ones where there's a supernova explosion going off. So you have to look at a lot of galaxies and then just pick out the ones that have the supernova going off in it. And of course, you want ones that are really far away as well. And this is an example of a supernova picked up by the Hubble Space Telescope. It's really red because of something called the cosmological redshift that we haven't talked about yet. That comes into play here in terms of the age as well. So again, further away something is, the further back in time we're looking. The universe actually, if you look far enough back in time, becomes very different than today's universe. You look far enough back in time, you look back to a time when there aren't any stars or galaxies. You look far enough back in time, you look at a time when the universe is filled with ionized hydrogen gas. The downside there is you can't see through it. You want to see ionized hydrogen gas, look at the sun. You can't see through it, right? So we can look back as far as that transition back to the time when the universe is ionized. Now we can see that light. The oldest light is redshifted light from that time period. And this is the so-called cosmic background radiation. If you've ever heard about that, that's what that's referring to. And so that's the oldest light in the universe. So if you can figure out basically that distance, again, that gives you an age determinant for the universe. The other funny thing about the universe is space itself stretches. This is the Hubble expansion, and the rate of expansion can be used to figure out how long the universe has been doing this. And so if you can measure this expansion rate, which is related to the redshifts, you can back out the age of the universe from the so-called Hubble constant. There's some additional things you have to take into account when you're measuring these distances. This expansion also messes with how bright something appears, so you have to pull that in, but we know how to do that. And the reason these galaxies are redshifted has to do with the stretching of space. Space itself actually stretches the wavelength of the light. So the light may start out yellow, but by the time it gets to us, it's going to be red if it's coming from a really long distance. And this is this redshift versus distance plot. This gives us something called the Hubble constant. The Hubble constant is actually the rate of expansion, but you can turn that around for an age, and that gives you a rough age estimate. Guess what? Right around 13 billion years. Okay? So we've got several techniques here that are self-consistent with the age of the universe. Now, strictly speaking, the expansion hasn't been constant the entire time, but we can observationally see how that expansion has changed over time. That expansion is also dictated by things like the amount of matter in the universe, by the amount of something called dark energy in the universe. So you fold all that into your model, you can extrapolate back in time in a better way than just a straight constant expansion. But you get about the same number. You get something in that 13 billion year range. You can actually pull age information out of this cosmic background radiation that I talked about. What this looks like, and what you're seeing here, are very tiny temperature differences in that hydrogen gas at that early time in the universe. What that looks like is very dependent on various parameters of the universe, including the age. So the combination of our current models for the universe with our observations sets an age for this expansion to be right around 13.8. Okay? Now this is model dependent partly, but we're really confident in the models. Einstein's general relativity, it's just a theory. Yeah, it's really a good theory. It gives you very good numbers with very, very high precision. If not, your GPS didn't work today. Okay? So not only do we have a timeline for the Earth itself, we now can build an entire timeline for this expansion history of the universe and the various phases that it's gone through. And again, you can literally look back to these various times in this expansion history. So if we put it all together and crunch it down to, say, a 12-month calendar, this is the history of the universe. Okay? So this is one of the great triumphs of science, is looking at this evidence, using logic and reason and the scientific method and pulling out what's happened so far in the history of the universe. So I'll stop there and I'll take any questions.